Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 37 on Electromagnetic Induction. So if you remember from last week, we talked about how moving charges produce a magnetic field and how a moving magnetic field, or I should say a changing magnetic field, produces a current. So we're going to have this setup where we have, say, a coil. I've got a coil here, and I have a magnet. So I've got this nice little north-south magnet here, a little bar magnet, and I'm shaking the magnet. And suppose I hook this up to a little light bulb, right? Okay. So before I have the magnet, nothing's happening. That light bulb is not lighting up because this loop of copper wire attached to the magnet, there's no voltage drop. So there's no current. Remember, if the voltage is zero.
Where's the magnet?
Well, that means the current is zero too, right? Because the resistance doesn't change. The resistance of this little guy, let's say he's 1 ohm, he's just there. But multiply that by 0, you get 0, right? Because if the voltage here is 0, there will be no current. If you think of it intuitively, it's like having a lake of still water. There is no current. We're having a loop of water, like a loop lake, but nothing's moving because everything is perfectly still and perfectly even. There's no voltage drop. There's no potential energy drop here to force the water to move. Well, what happens then when I bring a magnet and I start shaking it? And as I move that magnet up and down, I'm creating a changing magnetic field. And as there's a changing magnetic field, now I have a current. As I'm shaking this guy up and down, now I have a current that's moving and the light bulb lights up. There's also some really cool little setups, I wish I had one, where you have a light bulb attached to a wire and you start shaking a magnet near it and it will light up. Now, if you think about it intuitively, remember like we said with our lake, what's actually going on is it's as if you've got your ring lake, so it's just like a lake, like a ring shape, okay? So the water's just perfectly level, nothing's moving. Now if I come up here and I suddenly make a chasm open up here, the water's gonna start flowing. And then I make another chasm, although if you really think in this three-dimensionally, it's not so much like a chasm, it's more like I suddenly bend space and make this like into a waterfall. I change the dimensions. And then I change them again. So I'm changing it back and forth, back and forth. I'm changing like the terrain. Like imagine this lake and I'm just shifting the ground up and down and all of a sudden the water's flowing this way and then I shift the ground and now the water's flowing the other way. So I'm creating all this sloshing water. I went from a perfectly still lake to now as I shift the ground under it, all of a sudden it turns into this, say, the split lake, like a waterfall. The water's rushing down and then all of a sudden, say I bend space-time or whatever, bend the ground, and then all of a sudden I do it the other way, and now the water's running back the other direction, and as I'm shifting the ground and changing it, now there's a current, now there's a waterfall, because I'm shifting it back and forth. This is what shifting this magnet back and forth is doing. From the electron's perspective, it is the same as the water's perspective as that lake that I'm suddenly making, the altitude change for different parts of the lake. That's what I'm doing when I'm waving that magnet there. I'm suddenly making the potential change, and those little electrons are trying to move. Oh, whoa, now there's a potential drop. I got to move this way. Whoa, I got to move this way, move this way, move this way. This is alternating current, you'll notice, because I have to be wiggling that magnet up and down. So what's happening? Well, as I wiggle that magnet up and down, remember there's a magnetic field. Now, there will be no current if I just move that magnet and just sit it on the table. Like, this is just all sitting smooth. Nothing's happening. But as I shake that magnet up and down, if I shake that magnet up and down through that loop, what's happening is now this electric field is changing through the loop, right? Because as I push it down, then the field's like this, then I pull it up, and now the field's weakening, then the field's getting stronger, field's weakening. It's the same visually, if you imagine, as that still lake of water, where suddenly I somehow drop the ground from under here, and now I've got a waterfall, and now I suddenly drop this half, and this half goes back up of that still lake, and I drop the ground under it, and now it's got a waterfall, so it's like an earthquake where I'm shifting it back and forth. That's what's going on here, is I'm moving that magnet up and down. So the electrons are sloshing this way, that way, as the magnetic field is increasing in strength, as I'm dropping it through that, then the current will go one way, and then as I pull the magnet away, all of a sudden the magnetic field's weakening in strength, and now all of a sudden the current's going the other way. So the current's sloshing back and forth, and this is AC current. As I alternating current, well, AC, I guess, alternating current, AC, current, alternating current. But this is AC current here that I'm changing that field back and forth. Now notice, it has to be changing. For example, if I just split that lake and did it like this, all the water runs down, and then this is just empty. And now I've just got a still lake here at the bottom. That's like if I just put the magnet there and just let it sit. There will be an initial movement of charges, and then everything is still again. It's like if I split that lake in half, and all the water runs down, and now it's a still pool again. If I want there to be a continuous current to keep this light bulb lit, I have to be wiggling that magnet up and down, the same way that you can imagine my imaginary scenario where I split my lake in half, and it's rushing, and then I flip it the other way, and now it's rushing down this waterfall, and then I flip it back. Man, this board is getting really dirty. Can you give me oh, there it is. Okay, so now I just keep flipping back and forth, and then you'll see that I will have a constant current. So in the same way, I have to keep moving that magnet so that magnetic field is fluxing, weakening, strengthening, and that's what keeps a constant current. And yes, that current is actually flipping back and forth. That's why it's called alternating current. Really cool video I sent you out in the email where there's a guy who actually makes a setup with 2 different colored LEDs. You know, so 2 LEDs where their LED is like a one-way valve, and so you'll see as he's flipping the magnet back and forth, a different LED lights up because it's showing you the current's going this way, current's going that way, current's going this way, current going that way. Alternating current. Almost all the electricity we have in our homes is alternating current, and there are devices that will turn it into direct current that run on direct current. I mean batteries. Batteries are direct current. But almost all the electricity we get like through the wall is alternating current. We're about to talk about why, and it has to do with transformers. Giant robots. Just kidding. Transformers, but it's cool. Not quite as cool as giant robots, but it's so cool. Okay, so now we're going to talk about this little setup. Now you'll see that the more wire that interacts, the stronger the current will be. In the same way that if I manage to split many lakes with many waterfalls, there's more current, right? Okay, so this is not the best drawing, but if you imagine many waterfalls, many lakes, there's going to be more. So I can get more current. Yes?
Sorry, earlier I asked what were you just joking about?
About transformers and giant robots.
What were you joking about?
We're not actually learning about giant robots today. We're learning about electrical transformers and how we don't burn out all our appliances and why they send electricity at like 120,000 volts, but we only get...
What do transformers?
No. Transformers have to do... Here, Isaiah, we'll get to that. You be patient, wait, and then you'll see. Okay, so here I've got, if I take my circuit, instead of one little loop to my little light bulb, I decide to take that wire and make a bunch of loops, okay? And then go back to my light bulb. Well, now I'm getting a lot more current because there's a lot more little loops here interacting with that change. There's a lot more little conduction electrons and a lot more little loops that have to interact with that shifting magnetic field. So what I'm doing here is I'm actually making this way brighter. I'm getting a lot more current. I can even put multiple little light bulbs. A lot more current because I've got a lot more loops. And if you think about it from a molecular level, a lot more conduction electrons that are interacting with that fluxing field. And in fact, it goes perfectly proportional with one loop. If it gives you, say, 1 amp of current.
What if you have multiple magnets?
Wait. I got ahead of myself when I say 1 amp of current. Wait, we'll get to multiple magnets. I got ahead of myself there. Voltage. Let's start with talking about voltage. So voltage, remember, is like that shifting ground to that lake that I'm splitting in half back and forth. So the voltage, so if for every, if one loop got 1 volt out of that guy moving, the magnet moving, then if I have 1, 2, 3, 4, 5 loops of wire, now I've got 5 volts for that same magnet moving back and forth, because each little loop gets like that drop, that same voltage drop there. Okay, so you'll notice the more coils I have, the more volts I've got, the more voltage drop, and therefore the more current I've got, right? Because the bigger the voltage I've got here for the same little light bulb, the same resistor doesn't change here. So if the voltage goes up, then we know, hey, the current has to go up too. Okay, now, this might look like, hey, free energy. We'll just keep adding more and more loops and you get infinitely more energy. Not exactly. Because remember, someone is wiggling that magnet. Someone or something is wiggling that magnet. And actually, you can feel the difference. When you're trying to plunge, you have this hooked up to a little lead button. You have this set up, and you're just sending it back and forth through one loop. And then you make many loops, you will feel it resisting you so much harder. You are putting more work into that generator, where you're generating electricity. You're putting more work into it, shoving it through many, many rings is so much harder. You're producing way more current, but you can feel it. It's so much harder to put it through many loops. So it's not actually just, oh, we'll just add loops and boom, we get more energy. You are actually having to work much harder and moving that magnet through a lot of loops than a single loop. Okay, now we'll talk about Faraday's law. Now Faraday's law, my daughter wrote that. Okay, so Faraday's law is that the induced voltage in a coil, so the voltage in a coil that's induced, so we'll say induced voltage in a coil, is proportional to, that means as this gets bigger, this gets bigger. It's proportional to the product, so you multiply the product, so we product of the number of loops in our coil here, and the change, the rate of change of the magnetic field. They like to make B for magnetic fields. So I don't know why it's not M. I think it would be M, but it's B. B with a little vector guy on top. Little note here: when people are talking about electric fields, they often like to draw that little vector thing on top. And when they talk about magnetic fields, this is for electric. And when people talk about magnetic fields, they often like to do a B. Okay, so the voltage induced in a coil is proportional to the number of loops and the rate and the strength, really, of the magnetic field changing inside of it. So the bigger and more powerful, so I've got a much more powerful magnet here, line up many bar magnets. The bigger and stronger, the denser those field lines are. You can think of it that way. The denser those field lines are, the more, stronger the electrical field that is changing. The key, remember, is the changing electrical field, like that shifting in the link. The stronger the density and the strength and the rate at what is changing, or we like to draw this little triangle for change. If we do this little triangle, that's just the change in the electric field. Like the little triangle means change, the delta means change. So the rate at which it's changing, so the faster I wiggle it, the stronger this magnet is, and the faster I wiggle it is, the more the voltage induced in the coil. If I have a weaker, smaller magnet and I slowly move it, and this is smaller, then this is smaller, then I've got less voltage induced in the coil. If I've got a big, heavy magnet, really, really strong magnetic field, and I'm wiggling it faster and faster, the more voltage. Sweetie, is it still recording? Can you check? Yeah. Awesome. Okay. And
awesome,
in the same way, the more coils there are, the more voltage is induced. Remember? Because that's more little conductor electrons, more of those guys interacting with that fluxing field. Okay. Now, this thing about voltage, about Faraday's law, that the induced voltage is proportional to the number of loops and the changing of that magnetic field. That's true for the loops of anything. So I can make like loops of rubber, like a rubber hose. And look, I'm inducing so much voltage in this rubber hose. Why is it so much easier to wave my magnet back and forth through a rubber hose than say that it's hooked up to a light bulb that's not lighting up, or say hooked to a bunch of copper wires that it is lighting up? The reason is that while the voltage induced in both my attempt at making a circuit with a rubber hose and the metal one, same voltage, very different current. And remember Ohm's law, which is always true. So in the case where I've got my thing made out of rubber, the resistance of rubber is so big that even if I'm inducing a beautiful voltage here, I'm getting like no current, almost no current at all. And that's why we don't make our circuits out of rubber. we make our insulation, but inside of our wire, rubber wire is actually a metal wire. If you just have a rubber wire, nothing's going to happen. Because rubber has such a huge resistance, because remember, it's holding onto its conduction, it doesn't really have conduction electrons, because those electrons are tightly bound. And so that's why nothing's happening. So even if you induce the same voltage in a rubber setup, you're not going to see like no current. Whereas if you induce that same voltage in, say, copper wires, where the resistance is small, you can see a lot of current. So while this voltage induced by the number of loops and the flux and field is the same for different materials here, you're going to see a lot more current in something made of copper, let's say, obviously rubber is a far example, but even like steel wires. Steel wires don't conduct electricity as well as copper wires. That's why copper is so expensive. That's why copper is so valuable. People want the thing that conducts electricity so much better. And so because copper has such a low resistance, you get a lot of bang for your buck. For the same voltage, you get a lot more current. Which is also why it's really easy to plunge that magnet back and forth through the rubber, is since you're inducing like no current at all, you're not like it's like you're not paying. Even if you get that voltage isn't turning into money. That voltage is just sitting there. It's not turning into anything for you. Where here it is turning into something for you, and so you're having to work to get that energy. It's not turning into energy, I should say. So here that voltage is actually turning into energy for you, and that's why you feel resistance, because you're putting energy into the system by shaking that magnet back and forth. Okay. So now we will talk about motors. Now we very briefly touched on motors last lecture, and it's a little hard for me just with a whiteboard to really show you the glory of a motor. So I sent you guys some really cool visualizations, people using 3D models or whatever to show you what the inside of a motor looks like. And
what does this have to do with?
We will get there. Transformers. We're getting there. So I've got here a beautiful. Oh, can you give me that motor, baby? So one of my daughters really enjoys. She loves copper, and she loves to make copper jewelry. And she has discovered that she can get a lot of this wire from
a little bit
motors.
Too insane for paying more for copper than for gold.
Yeah, she likes copper more than gold. Well, anyway, so this, which is great because we don't have any gold wire lying around. All right, so this, as you can see, this is a motor, and that's exactly why there's all those coils here. Because what this is doing is that as the coils and coils and coils, all that electricity coming through, and then they vary it back and forth. And remember, moving charges produce a magnetic field. So it has here, you have a beautiful illustration here on you've got page 573 of your book. That's from last chapter. And you'll remember here, you've got your fixed magnet, you've got your battery, and you've got your loop with the bushings, the stationary bushings, but it's sliding over so that the current is constantly changing back and forth. This is when you have DC current, because it's a battery. It looks a little different when it's actually AC current, because then the current is flipping back and forth in the loop, and that helps it, keep going. But this is the same idea, the same principle. And so here you have your motor, and they have the current changing back and forth in all these loops of copper here. And with that fluxing, changing magnetic field, and then the changing, the changing fields and everything, and they turn this. And this is like the thing that was spinning, and I don't know what this was from. Do you know where Jenny got this from?
Grandma gave it to her.
I don't know which appliance this was from, but this was
She's
from an
had
appliance.
it for some time.
Right, but this appliance is turning electricity into motion. And it's got, I wish we could take this part apart. You see there's a little spindle there. There's a motor here. She got this from a dishwasher. You can see there was a lot more coils of copper.
Uh-oh, did it destroy the dishwasher?
The dishwasher was already broken. So sadly she had to cut the coils to get it off. You'll learn more about that later. When you open up these sorts of things, you sometimes see
Could these have some sort of thing that could kill us or not?
Not anymore. It's not attached to anything. There's no current running through it. But she got a lot of cool copper that way. Back to motors. So what motors are doing, if you remember from, I could draw this all over the table, but all over the board, but it's all here in your book, very beautiful, on page 573. Sorry, can they see it? Is that focusing?
Yeah.
So here you've got your magnet.
Well, we can't see the words.
Okay, here, I'll draw it then. So here you've got your loop.
This is what lecture been doing, okay?
So I think so, hope so. Here we've got our loop. And then we've got our giant magnet that we bent. So here we've got our bent, our bar magnets. So say this is north and this is south. So now we've got our these magnetic field lines. And remember, we need a changing electric field. Changing electric field induces current. Although here, and current, well, with motors, what we do is we hooked up a battery here. Right, so we've got a little battery with 2 terminals. And say I've put 12-volt battery, let's say. So here's the 2 terminals on my 12-volt battery. Okay? And so I've got a current going through my loop. Now remember, if we've got a current, we've got a magnetic field, there's a force that goes perpendicular. So that force on these little wires, pushing, it's twisting. But then, if it just twists into, well actually, to really show you, see, so you really need 3 dimensions. And it's actually looking kind of like this, okay? So you can think of it as the field lines are enclosed inside that loop. The field lines are going through the magnetic strength, and the magnetic field is plunging through those, you can think of it as through that loop, okay? And the more magnetic field lines, you can think of it this way, the more magnetic field lines that's enclosed there, that's the more the magnetic field. And then you've got a current, so you've got a current going this way and this way. And so remember, the current's going this way, magnetic field, so you've got a force on it, remember that's perpendicular, pushing this one, so it rotates. Well, what happens when it rotates, so the little guy rotates because there's that force on him, but now what happens when he is edge on, so I'm not doing a very good job drawing this because it's 3 dimensions, but imagine that you've got, none of those field lines are now going through that loop, because the loop basically used to be like this, used to be more like a, the loop used to be, like, say it was like a, rectangle, and the field lines are going through it, but now it's sitting this way, so there are no field lines going through it, okay? Because it's like all parallel. Well, now you've got the current, and the current and when the current and the magnetic field lines are going in the same direction, there's no force, right? Because remember, force to act on it, the magnetic field and the current has to be, the moving charges have to be in right angles from each other, and then the force acts on it perpendicularly. So when they're the same, when they're parallel with each other, there's no force on it. So if you just had your little battery, you think the little guy rotates, and it just hangs out there, and it's not going to move. So that's why they do this little thing with these like little contacts, and they have it on little bushings, little mechanism, that as these guys twist, it flips terminals. So as this little guy twists, and so then he's always twisting. It's so much clearer on this really cool 3D visualization model thing that I sent out to you. There's a lot of YouTube shorts on it, just look it up. How a motor works, a DC motor works. And so this is constantly flipping. Now, if it was an AC motor, remember, the electricity is going to be flipping back and forth anyway. But anyway, so that's how a motor works. So what a motor is doing, it is turning electrical, because it's turning this guy, and usually this guy is then connected to your food processor blades, or your fan and your ceiling fan, or something like that. So what motors do is they're turning electric energy, or the magnetic and electric energy, and they're turning it into mechanical work, mechanical energy. Okay? Energy, otherwise known as work. We're getting work done here. Well, work is force times distance and all that, but work. So we're getting work done here. We're having mechanical energy, and we're using our ceiling fan, the blender, whatever, powered by electric stuff. What is a generator? A generator is basically the opposite. So remember, a motor is we're taking electrical energy, magnetic and electrical energy, and harnessing it and turning it into physical work, like the chopping of your food processor, the swirling of your fan blades. But what a generator does is the opposite. A generator is we're going to turn mechanical energy. So what we're going to do is erase that battery. There is no battery anymore. And now we're going to hook this guy up to a light bulb, say in your ceiling or whatever. It's the world's ugliest light bulb. So close the circuit with a little light bulb, okay? So now we got a light bulb. We got electricity. So now this is no longer a motor. Oh, and now we're going to, instead of this chopped to your ceiling fan, now this is connected, say, to a steam turbine, okay? So your power plant. So now this is a steam turbine or something at your power plant, and it's turning, or say a water wheel, or say your wind turbine, and you've got something, and you're moving this, and you're forcing this little guy to rotate. Okay? So now you're forcing this little guy to rotate with your mechanical energy, whether that's a waterfall on a water wheel, or whether that's your steam turbine, and now you're lighting up your little lamp there. So what a generator does is a generator takes mechanical work, whether that is your steam turbine at your power plant, whether that is a water wheel that's turning, whether that's your little brother sitting there turning it for you on one of those little bikes, you know what those little bikes they have, where they're biking and it's producing a light. So whether that's your little brother putting in mechanical work, whether that is steam turbine from a power plant where you're, like, say, burning coal or something to boil the water, then the steam is forcing the fan blades to move, which in turn is forcing these metal wires here, forcing this little guy to rotate. When you force it to rotate, and then you get a current. And then you light up the light in your house. One moment, sweetheart. So you'll see that in that way, a motor and a generator are the opposites of each other, okay? Because a motor is all about turning electricity into mechanical work. See, a motor turns electricity, turns electric energy into mechanical energy, okay? And a generator is all about the opposite. A generator is all about turning mechanical energy, whether that's your little brother pumping something with his feet, whether that is you're boiling the water and the steam is forcing the turbine thing to move. So generator turns mechanical energy into electric energy. So this way, a generator is the opposite twin of the motor. And I highly encourage you to either look this up on, like, YouTube Shorts, where they have beautiful 3D models of how where you can see how the different motors and whatnot work, or even just look at page 573 in your book where you see the motor, electric motor, and then flip to page 580 where they show you the generator. And you see how they're the same thing. They just stripped off the battery and put a hand crank and put a little light bulb where the battery was. And here you've got a battery, and you presumably have whatever you're trying to turn mechanically, whether that's like the blades of your blender or whatever, is attached to this guy that's been forced to spin. Okay, but there's really, really cool visualizations and things on YouTube where they will show you how all those motors in your house work and how generators work, and it's very, very cool. Yes?
How much longer is it going to be?
I'll wrap this up, don't worry.
Okay.
Okay, so now we're going to talk about, so he talks a little bit about, like, he calls it the motor effect, the generator effect. What he calls the motor effect is when you are taking electrical energy and turning it into movement. So here example he has of that little U magnet, and you have that wire that's carrying current, and you force current through it, and then it starts to move, right? There's a force on it, so you've got the charges, the stationary field, with the moving charges, and now you've got your wire moving. So that's the motor effect. And then he calls it the generator effect when you do the opposite, when there's no current going through that little wire, but he starts to move that wire, wiggling it back and forth. And now you've got moving charges, because there are charges in the wire that are moving. So you have moving charges in the presence of a magnetic field, and then now you've got a force, but it's doing a different direction, because here the moving charges are the current, here the moving charges are when you're wiggling it back and forth. So you remember, the generator effect is when you are turning mechanical energy into electrical energy, and that movement, that force there is current that he's generating by wiggling that wire in a magnetic field. So the generator effect, remember, is mechanical to electrical, and the motor effect, remember, is electrical to mechanical. Okay, now we're going to talk a bit about transformers. Now, transformers are a way to basically move energy via the magnetic field. So here we're going to draw a picture. Okay, so here we've got two different circuits that don't even touch each other, okay? So I've got one circuit here, and say I've got, okay, and say I've got a really cool big battery here, okay? Let's say I've got, I don't know, 100 volt battery, okay? And there's a current going through this guy, all right? Because there's moving charges and there's now an electrical field. Remember, moving charges produce an electrical field. Okay, I'm sorry. There is now a magnetic field. Because we've got this magnetic field now that's being formed by all those little loops. I'm doing a very good job. You see it, okay? So I've got a magnetic field, and now I've got another little guy. So this guy, there is no battery. I just hooked him to a little light bulb, okay? There's no battery, so there's no current naturally going through him. But now that we've got an electric field, there starts to be current here, but only when that electric field is changing, okay? This electric field, it starts up, so the magnetic field starts up, and there is now a change, like the potential. It's like shifting the terrain again, so there's water flowing, but it will quickly find a new equilibrium, and then your little light bulb will go out because there's no more current. Well, if you want a constant current, you've got to be constantly changing. So whether maybe you're varying the electricity that goes through, maybe you have some sort of like a little switch, you're opening and shutting. So as you're making that magnetic field increase and die out, increase and die out, increase and die out, again, that's like shifting the ground. The water's flowing back and forth. Now you've got a charge, if that magnetic field is changing, oh sorry, wrong color. You've got that magnetic field growing and then shrinking and then growing and then shrinking. And now you've got a changing magnetic field. You know, the magnetic field is getting stronger, now the magnetic field is getting weaker. The magnetic field is getting stronger, now it's getting weaker. Now you've got that voltage shifting, that voltage change, and now you've got volts, and now you've got current, and now your little light bulb will light up. So what we're doing here is, in a sense, we're taking energy from this circuit, and by varying that magnetic field, what we're doing is we are that energy without even touching. These two circuits aren't even touching. But that magnetic field changing is shifting that energy from here to this light bulb. It sounds wild, but this is how all of our modern electric grid is based on. It's pretty cool. Now, it's even stronger, it's even more efficient to translate that energy if you put a big hunk of iron to connect them, because then the electric field is, remember how iron likes to line up with the magnetic field? So now you've got that fluctuating magnetic field connected, and so it just sort of concentrates. It makes it easier for it to translate. So it does work better if they're connected, but not in the way that we think of as charges or whatnot moving. They're connected in the sense of it's creating that fluctuating magnetic field that makes it easier for this guy. And usually when you see these things, this part is iron and this part is copper. So it's not relying on conducting electricity to light up this other guy. It's relying on the magnetic field fluxing through the iron to this guy. And I wish I had that. I had a beautiful, I don't even know what electrical appliance we ripped it out of. It must have been a transformer bit. But there was an iron chunk, and then there was these coils of copper over it, and this is what it was. But people found out the most efficient way. Engineers found out the most efficient way for it to move the energy from that one circuit to the other circuit was to take a chunk of iron that's shaped like a square donut, and then they wrap the copper. So here, doing a good job here. They wrap the copper, so we call it the primary coil and the secondary coil. So we wrap the copper. So we say we've got 3 loops of our primary coil, okay, and then say we've got 6 loops. 6 loops of our secondary coil, okay? Now, you might ask, well, why? Why bother? Why not just use this guy? Because of this. Hold on. The reason why is because, remember, if I put 3-volt battery, so 3-volt battery across this guy, okay, and I've got 3 turns, and I put 3 volts, this guy got 6 turns, I'm gonna get, so this here I've got 3 volts, now I've got 6 volts. Why? Because look, 3-volt battery, so see, I say I've got each of these loops as a volt. 1, 2, 3, 4, 5, 6, and I've got 6 loops, so each of those loops has a volt, right? Each of these loops has a volt. So it's because of the magnetic field going through here, there's a 1-volt drop for every loop, and because because of this iron chunk, I've got this nice little, so if you think about the number of magnetic lines going through these loops, it's the same magnetic field because we've induced this magnetic field. And so now for every loop on this side that has a 1-volt drop, this 3-volt battery, every loop here is also going to have a 1-volt drop. But now we got 6 volts. But this might look like magic to you. You might say, wait, this is just creating energy. How are you going to get more volts just by putting more loops there? The answer is the volts. Yes, you can. You can literally put 100 loops on this guy and get, let's see, if it's 1 volt per loop, you could get you put 100 loops on this guy and you could get 100 volts, and you're like, whoa, 3 volts to 100 volts. This would be called a step-up transformer, because you've got your energy, your battery or your power grid, whatever, sourced up here, and here you've got the thing that you're stepping up the voltage to. However, we're not just getting free energy here, because remember, energy, power, remember the joules per second, power, remember the power law? So the power law is P equals IV, right? This is current times voltage. Power equals current times voltage. This is the energy, okay? Remember, power is the work done, the joules per second. So we've got here, or the power time, anyway, we've got here, the more volts that I've got on this side, the power must be conserved. The energy has to be conserved. That tells you that the current in the primary, we're going to call this guy the primary coil, this is the secondary coil. So the current in the primary times the voltage in the primary will be the same as the current in the secondary times the voltage in the secondary. So here we've got so if we've got 3 volts here, right? The voltage here is going to be 3 volts times the current in the primary. And here we've got 100 volts times the current in the secondary. This tells us, just looking at this by math, that the current in the primary is going to be 30 times more current. All right, sweetie, hold on. 30 times more current. So if we've got 30 amps of current in the primary, this tells us that so that would be 90 volt amps, right? Then this tells us that this would be, if this is 90 volt amps on this side, and this tells us that this would be something like only 9/10 of an amp. We're only getting only 9/10 of the amp. So we've got way more amps going on this side, a lot more current going through those 3 coils. So while the voltage for our transformer, we step it up, we drop the current. The same with the step down transformer. When you step down the voltage, all of a sudden your current goes way up because the power has to be conserved. The current, see, the energy has to be conserved. So this way you'll find out that when it steps up, the current drops. As the voltage goes up, your current drops. And as you step on this side of the guy, you'll see as you step down, your current goes up. Yes, what's your question, sweetie?
You already did 37 minutes.
Okay, don't worry, Pumpkin. We'll wrap this up soon.
Okay.
Do you want to go have a cookie?
Yeah.
Go have a cookie. Or a candy. You can have candy from Mom's back. Okay. Okay. Now we will talk about, let's see, 37 point, sorry, I got my notes all over the place here. 37.1, 37. Oh, so now we're going to talk about power transmission. So you may have noticed those big, huge transformers that you often see, like sitting next to like massive power lines and things like that. The reason is because, remember we said that the current is much greater when the voltage is lower, and then because it has to equal this. But this does not violate Ohm's law, because this circuit equals V, follows Ohm's law, and this circuit, you might have said, wait, I remember from Ohm's law that the bigger the voltage, the bigger the voltage, the bigger the current. So why are you telling me? That's because this guy's following Ohm's law, and this guy's following Ohm's law. But when we compare them to each other, there's different resistances going on. There's different, like, this guy's following Ohm's law, this guy's following Ohm's law. Together, what connects this guy and this guy is this power law. Energy is conserved. So nothing is actually breaking Ohm's law. You just okay. So now remember that the reason like those really tall power lines, you see those big, huge. I'm talking about these guys look like this, and then you see those big huge power lines. These are actually traveling at something like 120,000 volts. Whoa, huge amount of volts. Why? Because they want to move all that electricity to your home. So what happens is it goes through a step-down transformer. It hooks up to your house, where if you're in America, your house is only getting 120 volts. If you're in Europe, it's 220 volts, okay? Let's just do a little American house here. So if you try to hook your things directly to 120,000 volts, all your electronics will blow up because they can't handle that many volts, right? So because they can't handle, if you put 120,000 volts on your little, home circuit, can you imagine the current that would tear through all of your circuits?
Would you die?
Massive circuit. I mean, probably your house would burn down. So what these little step down, when you see these like little, don't go in electrical step down transformer things, when you see them connected to these power lines, what's going on here is that they have, say they want to deliver, say the power company wants to deliver, so let's say you've got,
Is that what
let's say
your
you've got
electrical
20
box
circuits
is,
in your
Mom?
electrical box. Let's say you've got 20 circuits in your electrical box, and each of them can take 20 amps, okay? So that means that with 20 circuits, 20 amps, you want about 400 amps of electricity delivered to your home, okay? So if you want about let's make it easy on ourselves. Let's just say 1,000 amps. That's a lot of amps. Yeah, maybe you repair it. You got a lot of washing and dryers and ovens and I don't know. So say we want 1,000 amps, split up over your 20 amp circuits, but you want 1,000 amps delivered to your home at 120 volts, right? So they have 120,000, but the power law, remember, the energy is conserved. So the power of this guy is going to, has to be translated down into this for you. So what's happening here so to get this on your side, so you're the secondary circuit. So with you guys, so here remember we've got the power here, so we've got the current in the power lines, we can call that the primary, times the voltage in the massive power lines is going to be the same as the current, say here, split into your home, secondary, voltage, secondary. Now, it's not exactly like this because there's a lot of houses. It's not just you. You're not, all the power lines aren't, I guess, say we live out in the country and all those power lines are just coming out to us. One little house with all those wirings. Okay, so we've got this here and we're going to put in our 120 volts for our little electrical stuff and say we're using 1,000 amps. Okay, got a lot of high power things. Okay, so now we've got 1,000. So now we've got 12 with 1, 2, 3. So now we've got 120,000 volt amps that we're using here. We know that there's 120,000 volts in these power lines. So wait, sweetheart, what is it? Yes, very soon. So here we've got 120 volts, so how many amps are flowing through those power lines? 1 amp. A single amp is flowing through those 120,000 volt power lines, which gets converted with these step-down transformers, remember? It has to be conserved. The energy is conserved. Step down, and now we've got 1,000 amps to deal with of current. The reason they love to send power at these really, really tall voltage lines these huge, huge voltage, is because that way, if you only got 1 amp of current flowing through, it doesn't heat up your wires as much. Like high currents heat up your wires. Remember, you don't want massive amounts of current going through your wires where they melt. And you don't want super high current, so it's perfect that they both. And I just made up these numbers here. I think it's actually more like 1/10, a tiny, tiny piece of an amp is going through these massive, massive wires. And so that way their wires don't get super hot and melt, which would be bad. And it's easier to just step it down. So that's why they like to send power at super high voltages. Now, why do they always say danger high voltage? Remember, it's not the voltage that kills you, it's the current. It's the current flowing through you that heats up the wires. It's the current flowing through you that kills you. The reason is because, remember, you, as a little person, if you touch these wires, you have a fixed resistance for your body. I mean, it can vary if you're wet, if you're not wet, which is why, if you remember, V equals IR. If you, as a person, have a certain resistance for your body, the I, we don't want big I kills, right? So V equals IR divided both by R. So if you have a certain resistance of U, the bigger voltage that you get, the more bigger that current is. So if you make 120,000 volts, doesn't matter if you're super dry and wearing your rubber shoes and your little rubber gloves, even if you try to make your resistance big, if you've got that massive 120,000 volts, you're fried. That's if you touch, across the two of them. You are fried because that, no matter how big you can manage to get your resistance being bone dry and wearing your little rubber suit, if that voltage is big enough, there will be a current and you will die. So that's why you don't touch massive power lines. That's why when they space these power lines, they try to do it so that a bird's wingspan, bird can't short the circuit. Okay, so back to Okay, current, induction. Okay, so now we're going to just talk a little bit about what is light. Hey, don't worry, sweetie, this is the end. What is light? Oh, so first, okay. So remember when we said in Faraday's law? Oh, you want a bottle of milk? Sarah Grace, can you get her some milk? Thank you, pumpkin. Okay, so remember when we said that a changing magnetic field produces an electric field? Well, it's the reverse is also true. A changing electric field produces produces a magnetic field. So remember Faraday's law. So he restates it in a different way on page 587. And he said, an electric field is created in any region of space in which a magnetic field is changing with time. The magnitude, so the size of that created field, is proportional to, that means it will get bigger when the other thing gets bigger, or smaller when the other thing gets smaller, is proportional to the rate at which the magnetic field changes. The direction of the electric field is at right angles to the changing magnetic field. And this is actually true for the reverse. The changing electric field will produce a magnetic field at right angles, and so to the changing electric field. So what you end up with, if you can imagine it, so he tries to draw it like this. Okay, so here I've got an electric field that's changing. Okay, so it's changing direction and amplitude. It shrinks and then it goes in the other direction. It gets stronger and stronger, and then it shrinks, and then it gets stronger and stronger. Right? But as it is changing, remember, a changing electric field is producing a changing magnetic field. Where's purple? I really want to use purple for this. All right, we're going to just have to use black. And so remember, it's producing it at right angles. So as it's changing, it's producing a magnetic field. So I'm not doing a very good job with this 3D thing. Oh, thank you, sweetheart. But if you can imagine this being produced at right, this is supposed to be at right angles. Again, you can see on YouTube some really beautiful 3D visualizations of this. And so what's happening, so this is coming out. Sorry, I'll use purple next time. So as the electrical field is changing, it's producing a magnetic field that's changing, and they're just changing in opposite directions, or not really opposite, in right angle directions. And the motion, the force, it's going this way. So the entire wave is going this way, remember? Because the force, remember the magnetic field and the charges, and then the magnetic field going the opposite direction are in right angles, and then it produces the force. So the wave itself is traveling at right angles. All these guys are right angles to each other, right? The magnetic field, the electrical field, and then the motion of the wave. This is light. Light is a self-regenerating, because look, the magnetic field changing is producing a changing magnetic field, and the changing magnetic field is producing a changing electrical field, and the changing electrical field is producing a changing magnetic field, and so it is self-regenerating. This is light. This is why we call this class electricity and magnetism. Electricity and magnetism is light. It is light here. And for it to do just right, it's the speed of light. 300 kilometers per second. Did I get that right? No, 300. My brain is fritzing out today. 300,000. Did I say 300? Sorry. 300,000. That sounded too small. 300,000 kilometers per second. So this velocity that it's moving at, in a vacuum, 300,000 kilometers per second. This is light. And this is why light doesn't need a medium. It's not like sound. Remember, sound is those compression waves in air? Light can travel through a vacuum. Why? Because all light really is, well, I shouldn't say all light. Light is pretty amazing. I mean, it holds together causality. Basically, the fact that the speed of light never changes. I mean, in a vacuum. Obviously, it travels different speeds through different mediums. But in a vacuum, speed of light never changes, even depending on your reference frame. Light holds together so much. Light is like one of the most beautiful and strange mysteries, and we can explain what it is, but we can never explain all that it is. Light is truly amazing. And so light is this self-regenerating field of electricity and a magnetic field and electricity field, just traveling and just like always regenerating, always going on, through vacuum, through anything. And it's really, really amazing. Anyway, all right, you may cut the video.
Okay. Goodbye.
All right, Sarah. Did you finish?